Well, hi everybody. Thanks for coming to my talk, and thanks to the organizers for inviting me to this wonderful conference here. My name is Mark Stockett. I'm going to talk to you about my research I did during my postdoc in Stockholm University. This wasn't, of course, research I did by myself. There were a lot of people that contributed to the work I'm going to present today. Too many, in fact, to fit on one slide that you could read with such tiny print. So I've just put the institutions. I'm going to talk about experiments that were done in Stockholm and in Caen, along with some people contributing from Aarhus, where I am currently installed, and we rely heavily on the people in Madrid for their theoretical insights. I'm going to talk about large molecules, but what do I mean by large molecules? I mean molecules about this size, things like polycyclic aromatic hydrocarbons, fullerenes, or biomolecules. This is adenosine monophosphate. I won't talk about biomolecules today, though. Our main interest in this work is sort of astrophysics. So polycyclic aromatic hydrocarbons, these are thought to be just about everywhere out in the interstellar medium, out in other galaxies, floating around anywhere there's dust or hot matter. There you see these vibrational emission bands, and these are thought to be due to polycyclic aromatic hydrocarbons. But these are vibrational bands, and all polycyclic aromatic hydrocarbons have pretty much the same vibration bands because they have the same structure, these hexagons, the hydrogen atoms along the edge. So it's hard to say exactly if it's, is it large ones, is it small ones, what is the ionization state, are they in clusters? It's a bit of a mystery, but it's a mystery that maybe, experiments can help sort out. Fullerenes have been observed in space also based on their vibrational structure. This is a little easier because there are sort of fewer fullerenes out there in the world, so it's easier to identify the vibrational structure. And very recently, two electronic transitions were definitively identified as being due to C60 plus. These are part of the diffuse interstellar bands, a collection of, there's still 400 more that have not been identified in the interstellar medium, thought to be due to things like PAHs, but at least two are due to C60. So we know these molecules are in space, but how did they get there? What are they doing there? What's happening to them? What sorts of processes are they involved in? This is an extreme sort of environment, right? There's gamma rays, there's supernova shock waves which propagate through the dust where these molecules are found. There's high energy electrons, low energy electrons, solar wind, anything that you could throw at these molecules is happening. And somehow they're still there. But how are they processed? What sorts of interactions occur? What sort of processes are happening? And also, there's been for a long time some sort of speculations about there being a connection between these two classes of molecules. Can you start with a large polycyclic aromatic hydrocarbon and somehow fold it up into a fullerene, or can you blow up a fullerene into a more planar structure? There's been lots of speculation about this over the years. There are some experiments that seem to indicate that this sort of thing can happen, but what is the mechanism? How does this happen? No one knows. I'm going to talk mostly about non-statistical fragmentation of these large molecules, but what do I mean by that? I have to tell you what I mean by statistical fragmentation. Statistical fragmentation, this means that the fragmentation occurs sometime after the excitation, and such that the excitation is forgotten. You can have a collision with atoms, molecules, ions, whatever. You can have electron capture. You can have photon absorption. Somehow you put energy in, and then there's sort of a dot, 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 right? something happens, the energy is redistributed across the vibrational modes of the system, and then something else happens later. You can have photon emission, you can have recurrent fluorescence, for example, you can have thermionic electron emission, or you can have fragmentation. And this, in this case, would be statistical fragmentation, because there's been some sort of, the energy went into the box and came out somehow as a fragmentation. And when you have this sort of statistical fragmentation, the main products which you observe are the ones which have the lowest dissociation energies and the lowest dissociation barriers. Just because these are statistically the most likely ones you are going to see. I mean, this is why it's statistical. So for polycyclic aromatic hydrocarbons, the lowest energy dissociation channels are always H losses and C2H2 loss. And you can, this is an example. This is just showing you some of the energy scales here. I mean, you have some barriers that are, 4 or 5 eV, and you have dissociation energies that are 3 or 4 eV. And this is typical. And since these are the lowest energy channels available, these are what you see usually. So here's an example. These are experiments we did in Caen, where we accelerated helium ions to 11 keV and collided them with this anthracene molecule. And what you see is, this is C2H2 loss, along with some, and then you have the hydrogen losses are up here, and you have some other stuff which is due to, other processes like asymmetric fission or multiple fragmentation or fragmentation of multiply charged ions. But these are sort of the first steps, are these C2H2 loss and this hydrogen loss. One thing you don't see is the loss of very many fragments containing only single carbon atoms. You see always C2H2 or C2H3. You don't see C or CH coming out of these molecules. And because this is a statistical process, it doesn't matter what the excitation agent is. You see always the same thing. Here's electron impact. This is the same molecule. This is C2H2. This is the other stuff. Here's photoabsorption. Here's C2H2. And in both of these cases, there's no C loss. C60 is a pretty similar story. This is perhaps more well known. You always see this sort of evaporation of these C2 units. So you have always these chains, and there are magic numbers. There's structure in here. It's interesting. And you never see these, something like C59 though. You never have this C loss. And this is, this is some old spectrum from Aarhus, but it could have been from anywhere, right? It's a statistical fragmentation. It always looks pretty much the same. What I mean by non-statistical fragmentation is something like this. This is a fragmentation that occurs before the energy is redistributed across all of the vibrational modes. And you can see this in this simulation. You can see the C60 kind of breathing like this. And you can see, though, that this one atom is knocked out before it has a chance to do anything about it. So this is what I mean by non-statistical fragmentation. You could have other things that you might call non-statistical. You could have another name for this. But this is what I mean when I say non-statistical fragmentation. This was actually observed some time ago in Aarhus with C60, just this exact process you just watched. You have this single carbon knockout from the C60 cage, and you see a little bit of C59. These are from C60 anions colliding with helium and neon at energies 50 keV acceleration of the C60. Yeah, so that's interesting. And we also see this now in Stockholm with polycyclic aromatic hydrocarbons. In these experiments, we accelerate the PAHs into the helium target gas at much lower center of mass energies, 0.1 keV, compared to the Caen experiments I showed you earlier, which were 11 keV. The The gray spectrum here is the same spectrum I showed you earlier for the same molecule anthracene. And the black line is the Stockholm experiments. And you see there's a new peak here, which is zoomed in. Here you have this loss of some fragment containing only a single carbon atom. Here's just another example. This is con on the top with a larger PAH choranine. You still see you have the H losses. You have C2H2 here. You have your other stuff. You have no single carbon loss. Factor of 100 less energy in Stockholm. You have this huge single carbon knockout fragment here. This is, I mean, you know, almost half the total cross section is in this one peak, and then you have some small peaks here. And these look nothing like each other. This is statistical fragmentation. This is non-statistical fragmentation. What's the difference? Well, so here's just a quick schematic of the experiment in case you were wondering. It's in Stockholm. We have an electrospray ionization source, an ion, a lot of features. We select the ion we want with the quadrupole mass filter before accelerating it 1 to 10 kilovolt acceleration energy into the gas cell, where we collide usually with helium. So this gives you center of mass collision energies around 100 eV, and then we have an electrostatic energy analyzer. So why do we see, what's special about these collisions? How do you have this non-statistical fragmentation in these collisions where you don't see this with photoabsorption or electron capture? And this is because in the collisions you can talk to the nuclei of the molecule directly. So these are some simulations that were done by in the Netherlands, and you see the collision has already occurred here, and this helium is bouncing back, but you see you've stretched this bond. This one carbon atom has been stretched just to the point of breaking here, and this is not any normal vibrational mode that you're going to excite in any statistical manner, right? If you excite the electrons but via a photon and this is converted into internal energy, nature is not going to put all of its eggs in this basket, right? This is just not likely to happen. This is all the air going into your teacup. It's non-statistical. So in order to talk to the nuclei directly, this is a nuclear stopping process, right? This is hard sphere scattering. And so we go to our electronic and nuclear stopping theory to understand this. This I stole from someone's PhD thesis. But you see in the Kahn experiments, this is what's labeled experimental range here. We're up in these energy range, keV, few keV. And this black line, this is the electronic stopping. And you see this is large compared to the nuclear stopping, which is when you're hitting the nuclei. But in Stockholm, see, we're down here. We're at about 100 eV, right? And this is right at the peak here of the nuclear stopping. And so in this energy range here, we're going to have much more of this direct knockout than we're going to observe at higher energies where other electronic processes are going to dominate. So up here, we're going to have statistical fragmentation, and down here we will have non-statistical fragmentation. We've done simulations of this. So up top is the Kahn experiments, the high energy electronic and nuclear stopping. These are Monte Carlo simulations that we've done. And so you see the total stopping here looks a lot like the electronic stopping. But in our case down here, lower energies around 100 eV, you see the total stopping is completely dominated by the nuclear stopping. And the electronic stopping is sort of below 4 eV. I mean, it's almost not worth thinking about. And we can use these models to calculate cross sections, absolute total fragmentation cross sections, and absolute single carbon knockout cross sections. And you see these make sense. So we can do stopping calculations well too. And we also do classical molecular dynamics simulations. These are simulations where we actually model the bonds and we shoot the projectiles in and we watch the bonds break, and we can say exactly which trajectories The black areas are trajectories that lead to single carbon knockout. The red areas are where you deposit enough nuclear stopping energy to have a statistical fragmentation. You still heat the molecule enough for it to dissociate, but not enough in any one carbon atom to knock it out. And these also reproduce our experimental cross sections. These are with helium, neon, argon, xenon. But the interesting thing we get out of these simulations is they tell us the internal energy of the molecule after it's had one atom knocked out. And this is the key to understanding some of these experiments, because this determines the survival probability. If you knock out a carbon atom from one of these molecules, but it's hot, it's going to dissociate again, and you're not going to have this signature of this being missing one and only one carbon atom. So we have often this sort of two-step fragmentation where we can have this knockout leading to this big peak, but we can have this secondary fragmentation, which is a statistical process. So it's going to be a C2H2 loss, for example, or something else, but it's going to deplete this signature of the non-statistical fragmentation that we want to observe. And we also have competition from this statistical fragmentation where we don't have enough energy to knock out the atoms, but they're still hot. And we do DFT calculations to sort of understand the structures of these fragments that we're producing in these different two-step and multiple-step processes. So we have the knockout, the fragment relaxes, and then there can be a further fragmentation event. And this is too hard to read, so I've just showed in one example here. So we have a knockout. We've knocked out this carbon atom here from this coronine molecule. This fragment relaxes, and this is interesting. This has this kind of big void with this lonely carbon atom up here. You can imagine if you had a molecule like this floating around in space, it's going to be highly reactive. Anything else that floats along is going to get stuck here, and this can be a pathway to new larger species. But say it's hot, say you've heated it too much. You may have enough energy to lose this C3H2 group here, and then this fragment will relax. And what you're left with after two steps this is corannuline. This is a three-dimensional bowl-shaped PAH that you can form from this non-statistical fragmentation of a planar PAH. And this is interesting because it looks like one face of a C60 molecule, right? And this is one of these big questions that we're interested in is there a mechanism that can take you from a big PAH to a C60? And this is a bit mysterious because you can see, in this proposal that they're forming these pentagons and the thing slowly folds up. How do you form pentagons from hexagons if you can only lose two carbon atoms at a time? This is one way. Maybe there are other ways, but it's just an interesting thing to think about. This is just showing that this sort of survival probability idea. So as you increase the size of the PAH molecule, but have the same center of mass energy, this is 110 eV collisions with helium. This single carbon knockout peak in the gray area here, you see, gets bigger and bigger. So you go from with the smallest molecule, you have mostly a statistical pattern with a little bit of non-statistical fingerprint in here, up to coronine, where it's completely dominated by the non-statistical processes. And this is just because the larger molecules have more degrees of freedom over which to distribute this excess energy after the knockout, and so they're more likely to survive a given excitation. And you can also look at this by weakening. You can weaken the bonds of the molecule by substituting in a nitrogen. If you substitute nitrogen in, the CN bond is weaker than a CC bond, and so after a knockout, whatever is left over will be more likely to have this second statistical fragmentation step and deplete your single carbon knockout peak. So this is anthracene, all carbon and hydrogen. This is acridine with the one, and this is phenazine with two nitrogen substitutions. and this just goes down, even though the total fragmentation cross-sections are nearly identical. And so this is just, again, if the fragment after knockout faces lower dissociation barriers, it will have a lower survival probability. We see the same sort of thing with isomers. These are two isomers of C20H12. And you can see really what's happening here, right? The blue, you have less intensity in this peak, but it's showing up over here, right? This is the knockout peak, but the blue one has gone a little more over to this second statistical fragmentation peak. And this, we say, has something to do with somehow the overall kind of stability of the different isomers. And so we say that somehow the more stable of the isomers will lead to somehow, on the average, more stable fragments following knockout, and thus have a higher survival probability and give you a bigger peak in this knockout channel. Here's the energy dependence. This is the collision energy dependence for several values of the center of mass energy. You can see at the highest energies we have a pretty respectable knockout peak here for anthracene. As we go down in center of mass energy, this kind of melts away until it's kind of gone. You still have the statistical channels, C2H2, little C4. And for coronine, it's the same story. This knockout peak, even though it's still the largest peak, just sort of melts away. And this is the same thing, just on a graph. This is just taking the cross section for this peak, and this is the coronine, the larger molecule, and then these are pyrene and anthracene, two smaller molecules, and you can see there's sort of a threshold here, a common threshold around 30 EV, below which you do not see this knockout, and then it kind of goes up into a plateau. And we've modeled this with our classical molecular dynamics simulations, also more advanced time-propagated density functional theory methods, and we get a pretty good agreement on this threshold behavior. C60 is a little bit of a different story. I mean, I've been telling you that the more stable the molecule is, the bigger the signal you'll see in this knockout peak, but C60 we hardly see any C59. We don't see any at all actually in collisions with helium. We see a little bit in collisions with neon and heavier target atoms. But we see it, but why is it so little? I mean, you can see, first of all, it's just harder to hit a single carbon without hitting something else too. And it's also, it's probably that the C59 fragment is actually just very unstable or has some very low barrier to dissociation. Because you can see here in this energy dependence, we see we lose the C59 all way up at 160 EV, center of mass energy. There's no reason to think that the threshold for knocking out carbon for C60 is any higher than for a PAH. It's just that the energy deposit is going down. So this is the internal energy of the fragment after the knockout. This is for a PAH, but it should be the same for C60. It's highest actually at the threshold. The energy remaining in the fragment is highest near the threshold, and it goes down as you go to higher collision energies. More energy is taken away by the knocked out carbon atom. And so this is why this is just the survival probability of the C60 coming up. It's not that we're not producing the C59, it's just that it's all fragmenting on our experimental time scale. But this still has consequences, because if you have the C60 in a cluster, and these are experiments now done in Caen, where we shoot the helium at clusters of C60, you still have this knockout process that occurs, and the C59 is highly reactive. It reacts with a nearby C60 in the cluster and forms these dumbbell-shaped C119. You see it right here in the mass spectrum. And here's some movies. These were simulations done in Madrid. It's a little fast, but the C59 forms very fast. The knockout and the bond formation happen before the cluster dissociates. So this is a fast process. Here's just a zoom in of the C59 is on the left, and it bonds very quickly with the C60 that was sitting near it in the cluster. And then you have this now larger molecule than you started with. And we see similar things with PAH clusters. So here are experiments we've done with pyrene clusters. You see with hydrogen and helium projectiles. This is the monomer, this is the dimer. This is the sort of an analog of this C119. You've knocked out one carbon and you've formed a new bond between two pyrene molecules. This is this structure here. You go to heavier targets, the helium, you start to see even multiple things lost. And you go to heavier projectiles and you can form anything. You make a soup. You have even things involving 3 pyrene molecules. Quickly, to conclude, non-statistical fragmentation is important in collisions. Center of mass energy is around 100 eV. Stability of the parent molecule has an influence on the stability of the non-statistical fragment. And these fragments are highly reactive and can lead to new species in space. Thank you.